Hello, everyone. My name is Frankie Race. I'm a student from the University of Calgary. I recently finished an independent study with Jason Donovan as my supervisor on nuclear desalination. As global water usage increases due to population growth, developing countries, and changes in our climate, our global water stress also increases. Global water stress is the amount of available fresh water to the population. Different regions of our world have different water stress levels. As global water stress increases, an alternative source of fresh water is needed. That's where desalination is an excellent option. Desalination is the removal of fresh water from saline water, and it can be done using thermal or membrane processes. The thermal processes I've considered are multi-stage flash distillation and multi-effect distillation, and the membrane processes I've considered are reverse osmosis. Although there are other forms of desalination, these three are the most commonly used, and thus I've considered them for this project. Nuclear desalination is different from traditional or fossil fuel desalination as the power source for the desalination system changes. Nuclear desalination uses a nuclear reactor to provide heat and electricity. I've chosen to look at small modular reactors as they're considered the next generation of nuclear reactors. Small modular reactors range from 50 to 300 megawatts of electrical output. They're smaller in size with a lower capital cost, and they also have passive safety features, which makes them to be considered as meltdown proof. So for this study, I have looked at San Diego, California, as California is a high water stress state. It's also coastal, giving us a large option for feed water. I've looked at two different reactors. I've looked at XE100, which is a reactor from X Energy, and Moltex's stable salt reactor. These are two of many reactors currently under vendor design review from the Canadian Nuclear Safety Commission. So looking at the total potable water use for San Diego County, it varies. In January, they require 1.29 million meters cubed of fresh water per day. And in August, they required 2.11 million meters cubed of water per day. Looking at the XE100 reactor with the multi-effect distillation process, it would require 35 reactors in January and 57 reactors in August to supply the total potable water demand. This calculation was done using only the waste heat from the XE100 reactor, which is 125 megawatts thermal, and it's unrealistic. Nobody's going to have 35 reactors in a single facility. So I've looked at using a hybrid system. A hybrid system is using multiple desalination systems with a single power source. So using multi-effect distillation and the waste heat, and then reverse osmosis with the electricity produced from the XE100 reactor, we would require 3 reactors in January and 5 reactors in August to produce all of the potable water demand for a day in San Diego County. The other reactor I looked at is the Moltex's stable salt reactor. It has an electrical output of 300 megawatts, which is significantly larger than the XE100 reactor. This, partnered with the reverse osmosis desalination system, would require 1 reactor in January and 2 reactors in August to produce all of the potable water for San Diego County. Although these are only 2 reactors, they're very different, one with high electrical output and one with a low electrical output. Through this study, we've learned that hybrid systems are useful for reactors with high thermal output and low electrical capacity. We've also learned that the need for alternative sources of fresh water is increasing, and nuclear desalination is a clean option for fresh water. Although desalination can only be done in locations with ample amounts of seawater, the land area required is reduced with small modular reactors as they have benefits compared to traditional reactors. Although small modular reactors are not a reality yet, we're on our way, and hopefully nuclear desalination can be a part of our future.